Welcome back, everyone. In this video, we're going to continue learning about quantum numbers and orbitals. We're going to talk about different ways of describing orbitals in terms of their shell, subshells, and then talk about what rules dictate which quantum numbers are allowed, and then use that information to relate quantum numbers to the size, the shape, and orientation of an orbital. So to remind ourselves where we came from recently, we talked about how orbitals describe the probability of finding an electron in a given location. And remember how we talked about how not only does light behave as both particle and wave, but so does matter. So electrons, while they are objects, physical objects that have a specific mass, they also behave as though they are a wave. Therefore, we can't just say, where's the electron and describe it as one specific location. We can only talk about it as what's the probability of finding it in a given location because it's behaving as a wave. But once we can talk about its relative location, we can talk about the energy and the reactivity. So each orbital is characterized by 3 quantum numbers. We already talked about the principal quantum number when discussing the hydrogen atom. And the principal quantum number, n, describes the shell. And it provides information about the size or energy of an orbital. Those quantum number the values for the n quantum number can be 1, 2, 3, etc., up to infinity. The quantum number L describes this, combined with N and L describe the subshell. This is the angular momentum quantum number, and it tells us about the shape of an orbital. So we've indicated up here an N value and an L value, and the L value also has a symbol. So for L values, those range from between 0 to n minus 1. And so the most common ones that we'll be dealing with are an L value of 0, 1, 2, and 3, corresponding to S, P, D, and F-type orbitals. And I've indicated for you here S-type orbitals, P-type orbitals, and then also a D-type orbital. And you'll notice that S-type orbitals are all spherical in nature. The P-type orbitals, they have what we sometimes call a dumbbell shape. And then the D-type orbitals have approximately 2 dumbbell shapes or a 4-leaf clover. And so if we combine the information in the shell, the N value with the L value, that gets us the subshell. So you can have the 1s subshell, the 2s subshell, the 2p subshell, etc. M sub L is the magnetic quantum number, and this describes when combined with N plus L, it describes the orbital. The M sub L itself describes the spatial orientation of the orbital. So if we want to talk about a particular orbital, we need to describe its shell, we need to describe the shape, and then we need to describe the direction that it's facing. The values for M sub L are integer values that range between negative L and positive L, and they include 0. So, for example, we might say you have an N value of 2, you have an L value of 1, and you have an M sub value of negative 1. This describes a specific orbital. This describes an orbital in the second shell that is P-shape, and that is in this particular orientation. So when we look at P-type orbitals, we can have them on the X, the Y, or the Z axis. And so you can have P orbital like that, or like that. And each one of these orbitals corresponds to a same N and L combination. So this might be 2p, and then we could have 2p in the x direction, 2p in the y direction, or 2p in the z direction. And this x, y, and z subscript could is the same thing as the m sub l designation, which we could have be 0, -1, or +1. In this case, because our L value can be equal to 1. So there are certain, because of the rules for the quantum numbers, there's only certain combinations which are allowed. Again, to recap, we have n values, can be anything from 1 to infinity. Our L value can be anything from 0 up to n minus 1. And our m sub L value can be from -L to +L. So if we have an n value of 1, our L value must be between 0 and n minus 1. So that's between 0 and 0. If we have an n value of 2, then we could have an L value of 0 or an L value of 1. If we're in the third shell, we can have an n value, or excuse me, an L of 0, 1, or 2. Again, this is our n minus 1. This is n minus 2. And then this is 0. Then for our orbital values, those range between -L and +L and include 0. In the case of an n equals 1 subshell, L is 0, and so m sub L must also be 0. For n equals 2, we can have two different L values, and so there will be different m sub L values for each of those. When L is 0, m sub L must be 0. When L is 1, m sub L could be -1, 0, or 1. Again, ranging between -L and +L. And so then we see that same pattern repeated for when we have an n equals 2 value. Or excuse me, an L equals 2 value. And these relate to the various aspects of orbitals. Remember, we said in order to define the subshell, we need to talk about the n value combined with the L value. So how many n-L combinations are there here? Well, there's only one, and that we call the 1s. Remember that for L values, if your L is, we could have 0, 1, 2, and 3 corresponding to S, P, D, or F. If we have in the second shell, you have two subshells. You have the 2s and the 2p. The 2s corresponds to when L equals 0, and the 2p corresponds to when L equals 1. In the third shell, you have three different subshells. 3s for L equals 0, 3p for L equals 1, and 3d for L equals 2. Again, that's interpreting those different L values there. Now, we've defined the subshell. To define the orbital, we need to define the n, the L, and the m sub L value. And so we're looking then at each of these possible combinations. And so essentially, each combination of three quantum numbers describes one orbital. So we see that there's one combination of 3 in the first shell, and so there is one orbital. There are a total of 4 combinations, 2, 0, 0, 2, 1, -1, 2, 1, 0, 2, 1, +1 in the second shell, so that gets us a total of 4. And then in the third shell, we have the 1 orbital in the 3s subshell, the 3 orbitals in the 3p subshell, and then there's 5 combinations within the 3d subshell. And so if you want to add up the total number of subshells within a shell, we can do so, remembering that the combination of n and L values is a subshell. So we have then 3 subshells here. The number of orbitals is simply the number of orbitals combined in each of the subshells. Now, where do all these rules come from? Why must we follow them? Well, remember we talked about the Schrodinger equation, and that described how the wave function is related to the energy. In a similar way that you have a given mathematical function, there are solutions to that mathematical function where the function itself is equal to a certain value. Maybe it's 0, maybe it's 10, maybe it's minus 10. And so there is a certain, if we want the function to be equal to 10, there are certain x values that make that possible. Similarly, there are certain quantum numbers that are possible that describe the energy of the electron. And so that's what these quantum numbers are telling us. They come from the solutions to the Schrodinger equation that tell us the energy of the electrons. So now let's practice. I want you to try, I'm going to do this first one and describe it for you, and then after that I want you to try these on your own. So we want to know, are these quantum numbers allowed? N equals 1, L equals 1, M sub L equals 1. Well, the answer is no. L must be equal to 0 up to n minus 1. Since in this case L is equal to n, then that cannot be possible. Okay? You try the next one. Is this combination allowed? The answer here is no. The reason for that is because L must be 0 or greater. It cannot be less than 0. Third combination. Pause and try this one. Welcome back. So this one is not allowed. Hopefully you saw that that's because we said an n value of 0. That's not possible. What about here? In this case, n equals 2, that's allowed. L equals 0, that's allowed for when n equals 2. But our m sub L cannot be outside the parameters of negative L to positive L. We have an L value of 0, so m sub L could only be 0. Last one here. Pause and try this one. So this one can happen. We have an n value of between 1 to infinity. L value is less than n, but equal to or greater than 0. And so that is allowed. And then m sub L ranges from negative L to positive L. And so this is equal to negative L, so that counts. Okay, that's it for this video. Thanks for watching, and we'll catch you next time.